Okay, good morning Year 12. So this is the last lesson on hypothesis testing. So we're looking at using the p-value, which is another way of carrying out hypothesis tests. There are two methods, you need to know them both, and you could be asked to use either. Okay, so today we're looking at understanding what the p-value is, and then we're going to carry out a significant test using the p-value. Just be aware that p-value is not the proportion or the probability of success. It's a different p, which is why this is in italics. Okay, so just be aware of that. So up until now, you have solved problems or tested hypotheses by working out the critical and the acceptance regions. So you had your diagram, you worked out where the critical regions would be, you worked out where the acceptance regions would be, and then you looked at where your observed value fell, and that determined whether to accept or reject. So this method, we're going to use the p-value, and the p-value is the probability of x, okay, being greater than or equal to, or less than or equal to, our observed value, okay? And then we compare the p-value with the significance level, which is either alpha or half alpha for a two-tailed test. So the easiest way to see what that means is actually to have a look at some questions. So let's have a look at this question here. We've got when a coin is tossed a number of times, more than twice as many heads as tails are recorded. Using the p-value to test at the 5% level whether a coin is biased towards heads if the coin is tossed 4 times. So this is where we're going to stop here. We're just going to look at the 4 times tossed. Okay, so P is the proportion of heads when tossing a coin. Now that is not the p-value, that's P for proportion. Okay, and that's what our hypotheses are based on. So if the coin was fair, which is what we assume, remember the null hypothesis is what we assume to be true, we would assume the coin to be fair, then the null hypothesis would be that P is 0.5. We're asked to test whether it's biased towards heads, okay, and P is the proportion of heads, so we're looking to see if P is greater than 0.5 as our alternative hypothesis. Okay, then we want to state what our X is standing for. So X is the number of heads we would observe in our sample, okay, and X distribution would be binomial. N is 4 from here, and P is 0.5 because we're working under the null hypothesis. Now, in most questions, you'd be told what your observed value is. In this question, we've got to work it out a little bit, and it comes from this highlighted bit here, that we know that more than twice as many heads as tails are recorded. So if we're tossing 4 times, that's fairly easy to work out. If 0.5 was true, we'd have 2 of each, okay? So that's when heads and tails are equal. If it was 3 and 1, 3 heads to 1 tail, is 3 more than twice 1? Yes, it is. So our observed value is 3. Okay. We want the smallest possible value that will fit this, okay, and 3 is the smallest possible value. 4 would also be true, but we're looking for the smallest one. So the observed value in this case is 3. Okay, so what we're looking for. Here's my diagram that we've been using up until now. Okay, we're told in the question that the significance is 5%. And we know that it's a 1 tail at the top end, so this is where my diagram shows the top end. This region here is 0.05 for the 5% significance level. So what I'm going to work out is, where is 3? Is 3 in this bit or 3 in this bit? Okay, and I'm going to work that out by looking at what's the probability of being greater than or equal to 3. Okay, so we would start by looking at the probability x is greater than or equal to 3. We can't do that on our calculators, okay? So we can only look up less than or equal to. So greater than or equal to 3 is the same as 1 minus less than or equal to 2, okay? And if we use our calculator to do that, remember you need to be in your stat mode. For both calculators you need to be in your stat mode. In this one it's 2. We're then looking at the distributions and the binomial distribution, and in both calculators you're looking for the BCD, just because that's the cumulative one, less than or equal to. So the number of trials, we only want one probability, so I'm going to leave it as variable. Don't want it in a list like we have before. X in this case is 3, that's our observed value. No, sorry, X is 2 because I'm doing less than or equal to 2, so let's put 2 in there. Number of trials was 4. Oops. Put 4 in there. And P was 0.5 under the null hypothesis. Okay, let's execute that. And we get our answer as 0.6875. So that's less than or equal to 2. Okay. So I'm doing 1 minus less than or equal to 2, which is 1 minus 0.6875, which is 0.3125. So where would 3 be on this diagram if greater than or equal to it would be 0.3125? Well, I know this proportion here is 0.05. 0.3125 is greater than this, so 3 is going to be somewhere over here. Oops, let's get a decent pen. 3 is going to be about here, because greater than it is 0.3125, or 31% if you want to think about it in percentages. So when our p-value, so this is our p-value here, is greater than our significance level, we are going to accept the null hypothesis or not reject the null hypothesis. Okay, so remember this was our acceptance region here. So the statement we need to write is that there is sufficient evidence at the 5% level of significance not to reject the null hypothesis. If you put accept, that's okay, but not reject is what we're really doing, okay? And suggest that the die is not biased towards heads, okay? So the second part of that question was to look at the same thing, but with n as 24, having it tossed 24 times. So it's the same idea, same proportion. X is the same number of heads was observed, same hypothesis, but the binomial distribution has changed because it's now 24 and 0.5. So same as we did before. We need to work out the observed value. So more than twice as many heads as tails. Well, let's have a think about if I had exactly twice as many heads as tails. So let's say I had T tails, I would have 2T heads. So my total number of tosses would be T plus 2T, which is 3T, and that has to equal 24 in this case. Okay, so that suggests if 3T is 24, T is 8, and 2T is 16. So if the number of heads was exactly twice the number of tails, it would be 16 and 8, but we're told that there was more than twice, so our observed value has to be 17 as the lowest possible answer to that, and that's the one we're going to use. So observed value is going to be 17. So then I've got to work out, get rid of that. Here again, same diagram, we're looking at this end again, and this percentage here, or this proportion up this end is 0.05. We're looking at the probability that x is greater than or equal to 17, because we need to see if it falls into this bit here. So again, we look up 1 minus x less than or equal to 16, which is 1 minus 0.9680. You can do that on your calculator, and that comes out as 0.0320. So 0.03 is 3%. So that's smaller than this value here. So that suggests that 17 is around here. Okay, so it falls in the critical region. So there is sufficient evidence at the 5% level of significance to reject the null hypothesis and suggest that the die is biased towards heads. Okay, so that was the first question. That was a one-tail type. I want to look at a two-tail type now, because there's something's more to add to that. Okay, so this one, we've got a dairy company estimates that 60% of its products are sold within the EU. An employee believes this claim to be inaccurate, so she chooses 75 products at random, carries out a hypothesis test at the 2% significance level. She found 56 of the products had been sold within the EU. State the hypothesis clearly and calculate the p-value. So let's start with the proportion. So P is the proportion of products sold within the EU, and the hypothesis would be that H0 is 0.6 and H1, sorry, not H0, P is 0.6 and H1P is not 0.6. She hasn't said, or the employee hasn't said whether it's greater or less than 0.6, just said that it's different. So this is our two-tail test. Okay. So now we need to find the p-value, okay, but we need to state what x is first, and x is the number of products sold within the EU, and the distribution for x would be binomial, 75 because it was 75 products tested, and 0.6 because that's our null hypothesis. Okay, our observed value we are told is 56. Now the problem here is, I think I've got the diagram here, let's go to that. So observed value is 56 and significance level is 2%. Now what I want us to consider is it's a two-tailed test. Okay, so firstly significance is 2%, which means I've got to split that up, so it's 1% either end. But 56, I don't know whether I should be looking at this end and doing less than or equal to 56, or whether I should be looking at this end and doing greater than or equal to 56. So what I need to do is work out what's expected first, and expected is just working out the mean, and we do that by doing the 75 multiplied by the 0.6. So from your binomial distribution, you're just multiplying those two numbers together and getting 45. So 45 is what we expect to happen. 56 is above that, which suggests we're looking at the top end. Okay. So for a two-tailed test, first thing we have to split the significance up. Secondly, we need the expected value, and if our observed value is above that, we look at the top end. If our observed value is below the expected value, we would look at the bottom end. Okay, so we're looking at the property that x is greater than or equal to 56, okay, which is 1 minus less than or equal to 55. That's 0.99, 1 minus 0.99436, which comes out as 0.00564. So we've got to compare 0.00564. Is it greater than or less than 1%? And 1% is 0.01. Well, 0.005 is obviously less, and anything that's less means you are rejecting, because it would be in here somewhere. Okay, so we're rejecting the null hypothesis here, or not accept it. Yeah, no, that's right, I'm rejecting. So my statement will be there is sufficient evidence at the 2% level of significance to reject the null hypothesis and suggest that the proportion of products sold within the EU is not 60%. Okay, so that's two examples. Have a look through those again, maybe listen to the explanation again. When you're feeling fairly confident, I want you to look at pages 201 and 202 and exercise 2.2 and 2.3. Now it doesn't say to use the p-value method, but that's what I would like you to look at for these particular questions. They're designed for that method. Okay, so get those done, and then your next lesson is going to be to do the assessment for hypothesis testing. Okay, all right, speak to you soon. Bye bye.